Good morning, students. Today we'll start our last chapter, that is chapter 6, gas absorption and stripping. So, till now, what we have discussed, these are the fundamentals of mass transfer, okay, and thereafter we have discussed in detail what are the separation, major separation equipments to, that is packed bed and packed up and plate column. So we have seen this thing. Now we are in a position to discuss, learn the industrial mass transfer processes like absorption, distillation, leaching, humidification of this thing. So let's start with the first one, that is the gas absorption and stripping. So gas absorption is a mass transfer operation in which one or more pieces, that is solute, is removed from a gaseous stream, okay, gaseous stream by dissolution in a liquid. So which pieces I want to remove, that is called solute, and which liquid is used, that is solvent, and gas mixture. In a gas mixture, other than the solute, the remaining part, these are called carrier. For example, in the process of removal of H2S from natural gas using suitable solvents such as an aqueous solution of alkanolamine, okay, ethanolamine or methylamine. Okay. So here natural gas other than the H2S, that is called the H carrier. Okay, generally H2S is my solute and aqueous alkanolamine, that is the solvent. So these are the nomenclature. Okay. Generally, if the solvent is chemically reactive, which happens in this case of absorption of H2S with ethanolamine or methanolamine. Generally, H2S reacts with ethanolamine, and that is the chemically reactive. And if it is reacts, then absorption process will be fast. The rate of absorption of a gas is substantially enhanced if it is consumed by a chemical reaction in the liquid phase. So when I am absorption process mean gas liquid, okay, so solid is in gas phase, so it is getting absorbed in liquid phase, okay, so that other than this, other then solute will be separated from the gas mixture. So if solute reacts with the solvent, then that the absorption process will be fast, okay, and this is called chemical absorption, and it is faster than the physical absorption. Physical absorption is nothing but van der Waals forces, okay, and reverse of the absorption is called desorption or stripping. This is nearly as important as absorption. Very often loaded solvent is subject to desorption. By desorption, we remove the dissolved gas from the solution for further use of degeneration of the solvent. Just I have given the example that in a ammonia synthesis. So we have the feed carbon dioxide, nitrogen, and hydrogen. Okay, but for ammonia synthesis, I need nitrogen, hydrogen. So I need to remove this carbon dioxide. Okay, generally for this one, methanolamine or ethanamine is used. This is chemically reactive piece. So when the mixture is carbon dioxide, nitrogen, and hydrogen, I will use the solvent ethanolamine or methylamine. It will selectively absorb the carbon dioxide. Then hydrogen and nitrogen will be separated from carbon dioxide. Then nitrogen plus hydrogen, it will make the ammonia. Then ammonia plus carbon dioxide, that will make the urea. So I need to regenerate this. So for this one, what I whatever the carbon dioxide loaded amine solution leaving the absorption collage is strip of the dissolved carbon dioxide by using open sting. So if you take this and if you heat this thing at 60 degree, the desorption will come. Then what will happen? The carbon dioxide will be removed, and so I will get the ethanolamine again. So if I get the ethanolamine, then I can use it again. So this is the concept. So if you see that the carrier is nitrogen, hydrogen, and carbon dioxide. Okay, so if your mixture is carbon dioxide, nitrogen, hydrogen, here carbon dioxide is my solute, nitrogen, hydrogen is the carrier gas. Okay, then I am putting the ethanolamine. Okay, it will absorb the, what will happen? It will absorb the carbon dioxide, solute will be absorbed. Okay, it will come as a bottom product. So carrier gas nitrogen and hydrogen. Okay, this is the absorption. Then what will I'll put this thing in another. This is called desorption column or regeneration column or stripper. Okay. So I'll put the carbon dioxide up and ammonia, this thing, and I will heat it. If I heat this, whatever chemical bond has formed, that will break. Then carbon dioxide will come as a top product. So I am separating carbon dioxide, and this is nitrogen, hydrogen. So nitrogen, hydrogen make ammonia. Ammonia plus this carbon dioxide, we can make the urea. Now what will I then? I will get the what? I will get pure ethanolamine. Okay, then this, and there will be little bit loss. I will make up this one. Then again I will put this thing as a, so if you see ethanol amine is it is in the loop. Okay, I'm using this again, I am regenerate again, only the small part we are losing during the process, that makeup is required. So this is generally in plant that absorption and resorption regeneration column both are side by side. If you go any urea industry, okay, you will see this is there. Okay, but I can remove the carbon dioxide using image also. If I, let's say I have a nitrogen, hydrogen, carbon dioxide, and if you pass this gas mixture in NaOH solution, okay, then carbon dioxide will be removed. And in fact, the rate of absorption will be very fast, because carbon dioxide, it will form the sodium bicarbonate, which is sodium carbonate, which is much chemically highly reactive. But once sodium carbonate will form, you cannot regenerate it, isn't it? You need not to, you cannot regenerate. So that's the problem. So it depends whether I need the regeneration. If I need the regeneration, then I have to use ethanolamine. If I don't need regeneration, I need to remove carbon dioxide, then I will go the caustic soda. Okay, so this is the process according to need of this thing. Now, if you see in the absorption problem is in a gas mixture, I have to remove one solute selectively, whether it will be natural gas. Okay, natural gas I have to remove carbon dioxide H2S. If it is a synthesis gas, I have to remove the carbon dioxide or any other thing. Accordingly, it is the, if you take the generic case, there will be carrier and solute in the gas. So I have to remove this solute selectively using and solvent. So problem is I have to remove one particular solute from the gas mixture. Now solvent, which solvent I will use, it is in our hand. So I can select the particular solvent, okay, which will which will remove efficiently. And the selection of solvent, it there is some criteria are there. Okay, you have to always you have to see that I have used the solvent in such a way that it should remove effectively, and at the same time the cost of the solvent should be also, because money is involved there. Okay, so there is some select and criteria. One is solubility. Definitely right solvent is one in which the species says to be absorbed, that's the solute, is highly soluble, but it should not dissolve the carrier gas. So my what way I have to select the solvent, the solubility is very important. So which solvent I will use, only the solute will be absorbed, but no carrier gas will be absorbed. Okay, so that is the most, and rate of solubility will be fast. And sometimes that solvent is selective. I'm just giving one example. Let's take from the natural gas. So natural gas, what is? Let's take methane is there, carbon dioxide and H2S. Natural gas. Okay. Now but now when I use this natural gas in CNG station, then removal of H2A is necessary, because H2A is carcinogenic. But if you don't remove carbon dioxide, then there is no much problem. In fact, it will give you the value, because in a CNG station you don't know how much carbon dioxide is there. You cannot measure. So, so if I can use one solvent so that it will remove only H2S, but it will not remove carbon dioxide. That's mean it will add value to the company, because carbon dioxide is also going with the, as a CNG. So, but if you use ethanolamine, then both carbon dioxide and H2S will be. So this is the loss for the company, because carbon dioxide, there is no much no problem from the environmental point. H2S has to be. So if I use ethanolamine, both components will use of pure CNG oil. That is good. Okay, you are telling from customer point of that is good, but if you see from the company point, it is loss, because they carbon dioxide they are giving, but what CNG they are giving amount is less. So generally, the companies they sell they remove only the H2S. They sell the CNG as a mixture of carbon dioxide and CNG in pumping, because you cannot detect this how much carbon dioxide is there. Okay, that's the advantage there. So that's for the, so they don't use the ethanolamine. Instead of ethanolamine, they use N-methyl diethylene. So N-methyl diethylamine is one solvent which is very similar to ethanolamine. But this solvent has a capability to remove the H2S selectively, leaving the carbon dioxide. So that's why I'm telling which solvent I will use. That depends on the particular specification what is required. So for which CNG is going to the pumping station, only H2S remove, okay, then let it go, okay, then because it will get the, because carbon dioxide you are selling carbon dioxide at the price of CNG. So if you use the N-methyl diethyl, it is possible. Now let's take you are selling the CNG to the Palana power station. Now if company is selling the power station, because they will take the huge amount and they have a device, when you will sell they can measure how much carbon dioxide percentage is there. They don't accept, they will tell you I need only that methane. For that one you have to remove both carbon dioxide and H2S, because that is the criteria, because they have, if you give the carbon dioxide, they will tell, okay, this is this much thing is has come, so they will not accept this one. So for that one, for them, when you are telling selling this in Paladega power station, then you have to remove both carbon dioxide and H2. So for that one, for when CNG is linked to Paladega power station, use ethanol amine, because you have to remove both. But when you are selling the CNG to pumping station, okay, then you remove H2S. So this is the business strategy people, and for that one you see how one such selection of solvent makes the money. Okay, so this is then then another thing is a chemical reaction between dissolved gas and solvent added increases the rate of absorption substantially. But it is correct. But if you, I told that if absorption is chemically reaction, then dissolve rate will be very fast. That's mean separation process will be, but only if the reaction is reversible. The solute may be stripped out at a higher temperature in order to recover the solvent and solute and to the regenerate thus to regenerate the solvent. That what happened in case of a synthesis gas. So using ethanolamine, you remove this one from the mixture of hydrogen, nitrogen, and carbon dioxide. Then at this reaction is reversible. Then higher temperature, you stripped off, then carbon dioxide is gone. But if you use that's why I'm telling. If you use removal carbon, but for the purpose of removal of carbon dioxide from the aqueous caustic soda, which can be also used, is not used as a solvent despite of high rate of absorption attainable, because reaction is irreversible. So if carbon dioxide plus NOH, then sodium carbonate will form. It is irreversible reaction. Then you cannot regenerate. Okay, so that's the thing. You have to see the selection of solvent, but solubility is very important as per need. Okay, then second thing will come volatility. Solution, definitely that solvent should be less volatile, because if it is volatile, more loss will be there. So more makeup solvent is required, because no solvent will be used in loop. Okay, so it will be used for, then again it will be loop. So whatever the loss will be only if you there is a much loss of solvent, and the loss will be when it is highly volatile. That is the loss for the company. So the volatility will be as less as possible. Then viscosity also important, because the solvent should have a low viscosity, so that it flows easily. If you have a low viscosity, that's when your pumping cost will be low, because you have to for absorption regeneration all this you have to pump this thing. But fluid is high viscous, means your more energy is required to pump, so more money is required. So viscosity should be as low as possible. Then corrosiveness, that is very important for. So I should use one solvent, okay, so that should have a less corrosive, so that your equipment cost and maintenance cost will be low, because material of construction is very important. That uh, if you take, let's take, if you take the standard iron, okay, or normal steel, what is the cost? It costs around 200 rupees per kg. But if you take SS316, means high graded, it will cost will be 1200 rupees per kg. So the material of construction is important factor, and it depends on the it and material of construction. You select a based on the corrosiveness of the particular chemical used in this equipment. So if it is a less corrosive, then equipment cost will be low and maintenance cost will be also low. Then solvent cost. Okay, so solvent cost, you understand that if I get a cheap solvent with high capability. That is the always important factor. Okay. Then hazardous and toxicity. That is very important factor because solvent should not have a hazardous or toxic. It should be non-inflammable. That's the thing. So these are the different selection criteria are there. You have to according to then based on these selection criteria, if you have a you have to select, then you have to take the particular solvent of it. And if you see that what example are we are giving, there are number of some, but we are giving particular solvent for a particular process because these things are optimized. People have consider all these factors. They have seen that okay, this is the solvent can be used considering all these things to optimize the process. Okay. So now this once your solvent is selected, then what you will use this one to absorb for absorption process. Okay. And what has to be absorbed in a problem stream, that flow rate will be given to you. Okay. Let's take if you have to remove H2S carbon dioxide station for a particular oil of TNGCl, then what is the flow rate of CNG is coming from the oil? They will tell okay, this is the flow rate and that much carbon dioxide H2S is there and you have to remove. So in a problem statement, what will be the gas flow rate, it will be given, and that composition also will be given. So you know the flow rate of the gas and composition of gas. Okay, so that's mean you know that GS and what is Y. It is known to you. Okay, and then also they will tell how much removal is required. So let's say if you let's take it is a 0.1%, 0.1 or 1%, they will take 0.001, or it is a let's say 10%, they will tell it 1%. So how much removal is required, that is also Y1 and Y2 is required, is generally known from the problems and GS flow rate. Now what I have to do, I have to use this liquid, and which solvent I am using here, that is my choice. So what will be my motto? I will use minimum solvent flow rate to make the desired separation. So that will be our engineering goal. Means how much minimum liquid flow rate I will use so that I can make this separation process. Means whatever that they are specific without compromising the specification or quality. That's when this much is coming and this much has to be removed. Okay, so whatever is the outlet for it, it will be specified. So then what what how much solvent I will use and what will be my game. So I will try to use solvent as low as possible. If I use as low as possible, at small amount, that's mean my cost of operation cost will be low. Okay, so now but there is a problem, I will tell you. Okay, but no. So first you have to determine what will be the your minimum solvent flow rate. Okay, so how will you do this? So you know this was a steady state counter and mass transfer. If this is happen, GS equal to Y1 minus Y2 equal to LS into X1 minus X2, and Y1 minus Y2 and X1 minus X2 equal to LS by GS. Okay. Now the what is the concentration means Y2 is known to, because I told that it is known in problem study it will be known. Now X2 is known to, isn't it? X2 is known to because solvent, what is the composition of the solid? Generally X2 is 0 or point very small. Generally it will be known to it. Okay. So what is, but you want to determine what will be the minimum solvent flow. Okay. So that's mean the point 2 is known. So I know point P, this point 2. That is the this P. Okay. Now if whatever the my solvent flow rate, accordingly that slope will be there. Let's take I have some less solvent flow rate, so I will get this one. So this is point. Okay, particular, and I have this equilibrium line. Okay. Now if this is the happening, let's take this one. Okay, so if you have a that's mean P point is known 1, okay, a 2, and this is 1. Now what I'll if I decrease the solvent flow rate, so this slope will decrease, L will decrease. So this will shift to if I increase this. So this y2 x2 is known from this whatever the particular polymer. This is let's say because I have to remove up to this, so I have to come this. Okay, that will be x2. So now if I remove the solvent flow rate, if I decrease this one, that slope will decrease, so it will come to this. Now if I further decrease this one, then it will come to here. This is the when M line, this is the touching Q double dash, this is the equilibrium. So if I up to this, so it is because if I up Q double, so I am removing Y1, okay, but this is the solvent fluid and it is touching the equilibrium. That now if I further decrease the solvent flow, the slope will be here. Now if I slope here, so I am cutting this equilibrium line. So equilibrium line here means I can remove up to this. That much separation not possible. So after because I can when it is reaching the operating line is reaching the equilibrium, that's mean driving force is 0. So after that not possible. So if I decrease after whatever the solvent flow rate here, if I decrease further, then I will not get the separation y1. So I will go here. So that's mean what how much separation is required, y1 required, I am not satisfying. So what is really the minimum solvent flow rate? That is the this. Okay. So that will be where I am this. So that slope of this PQ line, what is this PQ double dash line? That is L minimum, LS minimum by GS. And for that one up you can go, but here if you see when you are here, your driving force is much higher, isn't it? But when you are going here, your driving force, particularly when you are reaching this point, then driving force is becoming low and low. That's mean that with this minimum solvent flow rate, we can remove up to y1 concentration. Okay, but tray that column height will be very high because if driving force is decreasing means your column height will be very high. So minimum solvent flow rate is one concept. So here you can determine the minimum solvent flow rate. At minimum solvent flow rate, the column height will be very high. That is also one problem. So if I use minimum, so that's but if you, my column separation column is very high, that is also problem. Okay. Because that is cost will be high. So I have to optimize both. So generally, people what do? People first determine the minimum solvent flow rate and then operating solvent flow rate generally 1.2 to 1.5 times of minimum solvent. So they will then this is the standard procedure. So this is one. Now let's take instead of this equilibrium line, equilibrium is like this. So 2 point is known to you. So if you decrease the solvent flow rate, it will go. But when you are coming here, after that you cannot. Then that's mean you are then you will cross the equilibrium. So you can come here, and that will be your x max. Here it will be your x max, isn't it? If you see when you are decreasing the solvent flow rate, your x1 max will increase, isn't it? X2, okay. X1, X1 max. So this way I can have that is, and that is very important. Okay. For a particular, when you are going to design on absorption column, so first you have to determine the minimum solve. Okay. And how will you do? You have to do like this. And this point where that operating line and equilibrium line are meeting, this point is called pinch point, because here the driving force becomes 0. Okay. Now if you take, okay, if you take the stripping, okay, in case of stripping, this that point 1 will be known to you, okay, and slope will be what? Ls by gs mean. Here I am removing this one, okay. In that case, I was making this ls low, so it was coming. But in this case, ls stripping means liquid flow rate will be given to, you have to, what will be the gas flow rate you have to determine. So I want the minimum. So if the point 1 will be known in this case, okay, and this is, let's take Rs on a particular slope. Now if I decrease this gas flow rate, the slope will increase, isn't it? So then if I decrease the gas flow rate, slope will increase, and again for a particular separation, whatever separation is required, whatever the thing. So when I'll reach, I'll touch this one, then this will be my minimum gas flow rate. So okay, so for absorption, I have to determine the minimum liquid flow rate, and for the stripping, I have to determine the minimum gas flow rate. So this way I will do this. Okay. So that is very important factor. See, when you are handling one absorption or stripping problem, your first job will be, you have to determine the minimum gas flow rate for absorption and minimum liquid flow rate for the strip. So that you can do through this. Okay. So let us stop today. Next day we will discuss the other part.